Assalamu alaikum warahmatullah. So as you know, last time we were talking about the very important thing, that's the conservative force. So we got a very important conclusion, right? When we talk about the conservative force, we can write down them as a negative gradient of the potential energy. Okay. So this is the thing that we discussed last time, where from this story comes and all that. Now here, it's a moment to know about this equation furthermore. To know about this equation furthermore, for that, I wanna just plot the potential energy term with respect to the position. Okay. So to make my the above equation very simple, I can write it as for a moment in a scalar form. As my f of x, it will be as d by dx of u of x. Okay. I put here, the notion like my potential energy right now, it only depends upon the one position. Okay, means it depends only upon the single dimension. So it's a one dimensional. Potential I'm just talking about here. As you know, to work in one dimension, it's rather simple than to work in extra dimensions. Okay, just two or three dimensions. So, as I told you, to know about more about this equation, I want to plot here potential energy, yes, with respect to the position. If this is my one-dimensional potential energy, and it just vary with the position. Okay. Let us assume here further, just like I got the curve, the potential energy curve like this. Any arbitrary curve I'm getting here. Okay. So basically, if I want to know the slope of this kind of variation, that will be represented by delta ux divided by delta x. Okay, this is how we define the slope of any curve under I mean under some condition as that all that. So here I got the slope. As you know, the slope is defined as the change in position of one variable to the change in position of another variable. So it's by the way, what we know from the rules of coordinate geometry and all that. But here I don't want to consume much more time on it. It's something that's understood here. But if I will just make the kind of limiting condition delta x tends to 0, as you know from the theory of differentiation, you'll get du by dx. If I want to know more exactly the slope of potential energy curve with respect to the position, okay, it is something du by dx, and du by dx is something that's present here. Okay, so by this way, it becomes very important for me to analyze how potential energy varies with the position and all that. Because when I want to know the slope is nothing but that's du by dx, and it is somewhere present in this equation. After writing this equation in its most simpler form and all that, so I got the slope here. The slope is basically du by dx, and when I want to know the force, I have to multiply it by minus 1. Okay. When slope is known for me in the potential energy variation with the position, I will just multiply the negative minus 1, and I will get the corresponding force here. Okay. So this is why basically the things becomes important for us and all that. When we look for this kind of variation, I got slope, but slope is here nothing but du by dx. Okay, to use some limiting condition and all that, as you know it. So, but at the same time, this du by dx, it is related by means of the force. Generally, when we talk about the conservative force and all that, so when is the slope will be known for me, I can just figure out that force. Okay. So this was something very important under how potential energy, it will vary with the position. At the same time, this variation is nothing but it's the slope of the potential energy curve. And when we switch this slope here, we have to only multiply it with negative minus 1, and I will get the force. This is a good news for you in a way when you know the slope of the potential energy curve with the position, and at the same time you can know the force chi. Okay. This was something very important to mention here regarding the variation of the potential energy with the position and all that. So here, there is something very important right now to discuss. Just like when we talk about the force here, just like if I want to know what in which direction the force will be at any point, this is something that's very important and very simple at the same place. Just like here, if I want to know the slope here, it is something, if I will do the tangent here, it is here, means that my du by dx, is positive here, okay, because it's increasing slope here. At the same time, when my du by dx will be positive, force will be negative, okay, force will be negative here, okay. So force x slope of the force, and basically if I have to know how exactly in which direction around my force will be, it's something that's very simple to know for me from this kind of analysis and all that. Just like here, if I want to know my slope, that comes out to be positive here. At the same time, if I want to know the force will be negative by means of this equation and all that, okay. So at this point, basically my force will be in this direction, okay. I hope that you are getting it. Not only this, if I want to know here, basically slope is here, what we can say, du by dx, it's, if I want to know it here, it's something like less than 0, okay. When it's less than 0, negative of negative, it will be positive. My force at this point, it will be in this direction. I hope you are getting it, okay. So if I will just, make my analysis here further. So I got here, at any point I can draw the direction of force. At the same time, I can find its magnitude. Its magnitude will be found by means of du by dx. Magnitude of du by dx, by this way I will get precisely some number, okay, that represents the magnitude of this force and all that. So force is something like vector. It has both direction as well as the magnitude. From this kind of plot, we will get everything. Only thing is that should be known to us, that when we talk about the variation of the potential energy with the position, if slope will be known to us, we can find everything regarding the force guy and all that, okay. So on further analysis of this issue, what what will be my next point of interest here, if I will just mention the more simplified form of above equation, I will again treat here my one-dimensional force, okay. It will be minus d by dx of u of x, okay. Hope you are getting it. It's again, I use here the simple potential of type 1D, okay. So here if I will assume that the force basically is 0. If f of x will be 0, what it means force will be 0 only when the slope of the potential energy curve will be 0 with respect to the position, okay. So if I will just consider the same analysis here once more, I will get something more here in a way, just like if I will just plot the potential energy with respect to the position here once more. If this is my potential energy line here, if this is the respective position of the particle at any instant of time and all that. So here, if I will just mention my curve here like this, okay. Look, precisely if I want to know the slope at this point, it will be 0. The slope at this point is 0 because potential energy is going to be constant here, and slope at this point will be 0. Again, the potential energy will be constant here. When my slope of the potential energy curve with respect to the position, it will come out 0. At the same time, more safely, I can say that my force will be 0, because force is something like, first of all, it has been, dependent on what we call as the slope of the potential energy curve, okay. If slope of the potential energy curve somewhere comes out to be 0, means that in turn my force will be 0. So I can easily say that the force at this point, suppose I will just label this my point A, this is my point B, force at this point, it will be 0, force will be 0 here, and my force will be 0 here, okay. Not only this, when we talk about the force which are going to be 0, at the same time, our system will be under equilibrium by means of force, okay. Very important, equilibrium by means of forces. If the force equilibrium position, if the force equilibrium condition is being satisfied, means body is not under the action of the force, okay. So when force basically vanishes here, so if I will use here once more this equation, and this kind of content stuff here is very important in a way to analyze. So my f of x, it's again d by dx of, yes, u of x, okay? Again, I'm choosing here one-dimensional potential. It's something I told you to make my analysis very simple through all respects and all that. So here, look. When I talk about my force is going to be 0, means that my du by dx is, it will be again 0. It will be again 0, yes. So what it means is basically my potential energy is constant. My potential energy is constant. Okay, potential energy can have the constant value here. But this constant is minimum of the potential energy. It's the minimum of the potential energy. And this, if I would just have the graphics like this way, so I don't guess where the maxima of the line will have, maxima of this potential energy line will have from this way around, okay? Because graph is going to be infinite in this fashion. So here, but more specifically, I can say that this point is the point where my potential energy seems, what I can say, the maximum, okay? So I told you as before, here potential energy is going to be constant. Here it's going to be constant, but this constant of potential energy represents the maximum. It's a u max, and it's a u min. U maximum and u minimum, here I got from the graphics. At the same time, whether we talk about the minimum potential energy or the maximum potential energy, both the cases my force will come out to be 0, okay? So when my force will be 0, I told you that I just look for the kind of equilibrium position at the same time when somewhere the force is going to be counterbalance, okay? So our system will be in a sort of equilibrium by means of force, and I should look for those equilibrium points, okay? So, but here I just name these kind of equilibrium points as here when my potential energy is minimum, obviously force will be 0. I will get the point. I will get equilibrium point. Okay, I will get the kind of equilibrium point. But this equilibrium point is known as a stable equilibrium. Stable equilibrium. Okay. This position will be the most stable position, okay, and it's a kind of equilibrium position. I call it's a stable equilibrium position because my potential energy is minimum and force is 0, okay. So when my potential energy is minimum, the corresponding point will represent what we call as a stable equilibrium, okay. Not only this, when we talk about yes, a maximum potential energy. For a particle, if it has a maximum potential energy, the corresponding equilibrium point, I call it's an unstable equilibrium. Unstable equilibrium point, okay? So unstable equilibrium point will be here. My potential energy is maximum, force will be 0, but this point A will be yes, it will be in an unstable equilibrium. So that if I want to, give an example of the stable equilibrium. So suppose we have a kind of object, okay? That's been connected by means of the thread, okay, but the object lies on some horizontal floor. So it's a time when we call some situation like, when we call some configuration like it's in a stable equilibrium. At the same time, if we have the pen here, okay, and this end of the pen means the more sharper end of the pen, it's lying somewhere, but it's going to be lie in a vertical way, okay. So this is again the equilibrium position, but when I will just perturb its base by feebly, okay. At the same time, the pen will fall. It represents what we call as a kind of equilibrium, but that equilibrium is what we can say the unstable equilibrium, okay. In addition, there is one more type of equilibrium when we just going to make the plot of potential energy with respect to the position. That's what we call as a neutral equilibrium, okay. Neutral equilibrium. Neutral equilibrium, okay. Neutral equilibrium, basically it's a point or it's a region where the potential energy is flat from either side. Just like how we can, I mean, show the equilibrium position for a particle in a potential energy curve. Here, if I will just rub it for a moment to show all points here, but more specifically, I will first of all look for the neutral equilibrium. Neutral equilibrium point is a point where the potential energy is flat. Okay. See, at this time, potential energy is flat on either side. If I go this way around or this way around, potential energy is going to be flat. Okay. So these points are basically, I can say, these are what we call as neutral equilibrium points. Okay, and this is my, I mean, unstable equilibrium point, and this is my stable equilibrium point. Okay. This is my stable equilibrium point. Okay, but a given potential energy curve, it may have the number of minimas and the number of maximas. That's not something, I mean, very difficult to analyze here. Once you know one maximum point, you can look for another maximum point, or so on and so forth. But the important thing here is mentioned more specifically when we can say something as unstable or stable, or we can say the neutral equilibrium point. This is, I mean, the situation where we can say something as like it is going to be stable, unstable, or neutral equilibrium at every point. At every point, my force is going to be zero. Okay, my force will be zero, and the potential energy will be minimum, maximum for stable or unstable equilibrium. Okay, for neutral equilibrium, my potential energy is going to be flat. Okay, means when my potential energy go, it is going to be flat on either side. I can say such a region is known as neutral equilibrium region. Okay, so neutral equilibrium region, it's not a kind of, we can't say it's a kind of stable region. Because when we place the particle under the neutral equilibrium region, particle may move freely according to Newton's first law, because somewhere the force vanishes at every equilibrium point. By means of force, the force vanishes. So we can say the neutral equilibrium point, it will not in general stable. So, I mean, when we just make the implementation of this curve, it fits what we call as when we discuss the van der Waals force. Van der Waals interaction. Okay, van der Waals interaction, it's a type of interaction where we can look for the neutral equilibrium point. Okay, when we have two particles, when basically my position, basically when we potential energy, it will be obviously it is going to be vanish when the separation increase. As the separation increases, the effect of potential energy will decrease. Okay, the moment when we discuss the neutral equilibrium point, basically again my potential energy will be first of all very less, means that again we are facing the kind of zero potential region. Okay, in a way, to understand that basically when we talk about the neutral equilibrium point, it's not in principle the kind of stable point. Okay, because when we just discuss the van der Waals type of interaction, how their potential energy changes. Okay, and there is a kind of good discussion. Basically, it has been observed that the potential energy, it varies with inversely as a square of as an x to the power 6. Okay, so when we discuss the neutral equilibrium point where the potential energy will be more or less flat, okay, at the same time when the separation will increase, okay, I'm talking about here the van der Waals interaction, we come across this kind of conclusion there. So when we just fit this kind of potential energy variation with the position in case of the van der Waals interaction, we come across a point that's what we call as a neutral equilibrium. I told you as before, neutral equilibrium is not maybe the stable, because when we place the particle in the neutral equilibrium region, particle may move freely according to Newton's first law, because the force is zero there. Okay, so this was about how we can look and figure out what we can say the stable, unstable, and the neutral equilibrium positions when we talk about how potential energy varies with position and all that. Not only this, there is one more thing that's, I can say, the pending here. If I will just remind my force equation here once more in the simplest form. I'm getting here d by dx of is u of x. First of all, I want to tell you, in the last moment, I use here the partial derivative, dou by dou x, okay? Whether you use an ordinary derivative or the partial derivative, you will get the same thing, because I mentioned at the first place, my potential energy, it's something more or less one dimensional, okay? So you can replace this partial derivative by an ordinary derivative. That's why I use it here. No issues here, okay? So here is the moment to discuss something more about. Again, I will just mention here the plot of potential energy with respect to the position. Look, if I can add or subtract some constant to the potential energy, it has no effect on force. Force will be again zero, okay? But it will change our entire potential energy function. How? Here, if I will just add some constant to the potential energy, okay, it will move up my potential energy curve, okay? At the same time, if I will subtract some constant to the potential energy, it will move down the potential energy curve, okay? Like this way, we may have the series of, or is it the infinite number of family of lines here, okay? I'm just somehow worthy to sketch it in a more proper way, but the idea is very important here. What I mean to say here, so far, if my potential energy is here, I am going to add some constant to the potential energy. At the same time, I can subtract a constant to the potential energy. It has no effect on what we call the force, okay? Because if we differentiate, the differentiation of constant is zero, again, I am getting at the same thing. But it will entirely change my potential energy function. Either it will move up or move down my potential energy function. As a result, I have the number of potential energy curves, okay? Family of curves will have the same slope. This was again the important bit to mention here. If we add or subtract some constant to the potential energy, the slope of potential energy curve will not change, okay? This was something more here to mention. So here, if I'll just discuss the problem which is based on what we can say, if there is a kind of variation of potential energy with the position, like here, okay, here. If I'll just consider this kind of variation here, if there is a one-dimensional potential energy, it varies with the position like this way. If there is a point A given in a question and there is a point B given in a question, I want to know whether what will be the force at point A and what will be the force at point B, okay? Only what will be the sign of force? Will it be positive at point A or B? Will it be positive at point A or here? Will it be negative here, negative here, negative here, positive here, negative here? These are the kind of four options, and I need to figure out which kind of combination will be suited for, okay, in a given expression. Like, to know the force, first of all, I will just look for the slope of the curve first of all, okay? If I will draw the tangent here, that will give me the slope, okay? And the slope at the point A, is basically what I can say. It's less than 0. Slope at the point A is less than 0. Negative of the negative slope means that force at point A, it will be positive, so it will be in this direction, okay? So FA will be in this direction because it's a positive direction of force, okay? At point A, my force is positive, okay? At point A, my force is positive, so I can eliminate these two options. So I can look for option first and fourth here, okay? Now, if I look to the point B, first of all, if I know what the slope will be increasing here. So my du by dx at point B, it's positive. So the negative of the positive, it will be negative, okay? So at point B, okay? At point B, basically, what will be my slope? Yes, my slope will be negative here. Sorry, my slope is increasing here, but at the same time, I can look for my force. My force will be, yes, it will be in this direction. Okay, at point B, my force will be in this direction. So I got here one thing like very important, very important. When we talk about the potential energy will decrease in the direction of force. The potential energy will decrease here in the direction of force. How we can analyze this bit? This was a question which basically was in the mode to ask us what will be the nature of force at the point A and the point B. My force at the point A, it will be positive because slope is downward, it will be negative, negative of negative will be positive. So I got force at point A, it will be positive here. My slope is here positive, but the negative of positive will be negative. So here the option, I can say the fourth is the correct one, okay? Not only this, I told you as before something very important. When we talk about the force, okay, potential energy will decrease in the direction of force. When we move in the direction of force, there will be the corresponding decrease in the potential energy. There will be the corresponding decrease in the potential energy, okay? Because when the distance increases here, distance will increase. So when the separation will increase, obviously the potential energy will decrease. By this way, we can understand this. This force, it will tend to put this particle in this way, but at the same time, my potential energy will also decrease. Okay, these are the two conclusions I can get here. Either it will stretch the particle along this way, or it will move down the particle along this way. But under both the cases, my potential energy will decrease when we talk about the force. Okay. So how we can know it more effectively? I will use the kind of variation with the potential energy. That's a well-known variation. In the future discussion, we will come to know how exactly that variation will be. Yes, if I have the kind of symmetric variation like this, okay. So my potential energy curve, it is symmetrical about the origin. Okay, from either side of origin, I got the kind of symmetrical variation of potential energy with respect to the position. Okay, if I want to know the force here and the force here. Again, it is my point A and this is my point B. So if I will draw some dotted line to represent my point A here, this is my point B. Okay. First of all, if I will just look how potential energy changes to distance, what's the kind of proportionality? Look. To know this kind of graphics more effectively, I will use here the kind of idea like, again I will use my potential energy variation with the distance. Suppose if the graph will be look like this, means that my u is proportional to x. Okay, but what's happening here basically, when u will increase, this is the line along which the u increases, and this is the line along which the x increases. So x increases more than u. As u increases, x also increases, but x increases more than u. It's a kind of means the potential has the kind of quadratic dependence on what we can say the position. It's a kind of concave curve. Okay. So the potential has basically the kind of quadratic dependence on the position. Okay. Look. If I will see here, if I want to know the slope of the line here, it is in this direction. Okay, means that the slope of line is here increasing. My du by dx is here greater than 0. Okay, when du by dx will be greater than 0, what it means then my slope is here increasing. If I will use again the equation here, and d by dx of is u. Okay, because in this quadrant x is positive, u is positive, I will get the positive slope by this way, because my line is going to be increased at this point A. So du by dx is positive here. At the same time, my x will be, my f of x, it will be negative, means that my force will be in this direction. Okay, not only this, when we talk about the point B here, but I will absorb the negative values of x. So here again there is an increasing slope. Okay, there is an increasing slope here. So when slope is increasing here, no doubt slope is increasing here, but what will happen here basically? Yes, my x is negative here. When my x is negative here, this will be negative of negative, it will be positive, means that my force, it will be in a positive direction. It will be in a positive direction. Okay. See, in the direction of force, there is a direction of force in this way, and there is a direction of force in this way. In the direction of force, what will happen basically? If I look at this kind of plot here, it seems that my potential energy, it varies with this square of position. Okay, means there's a kind of quadratic dependence of potential energy on the position. So when we move along this way, what will happen to the x? Yes, it will decrease. When x will decrease, what will happen to the u? It will decrease. So I got the kind of conclusion, when we move along in the direction of force, there is a decrease in the potential energy. Not only this, when we talk about here, what happens to the magnitude of x? No doubt there is a negative value, but du by dx, yes, or I can say my potential is again here, it is something, okay, so it's something the norm square of x. So again, if I look in the direction of force, to avoid the confusion, I use here the negation. Again, even though if I put here negative sign, it will be again positive, okay, by symmetry and all that here. But what's my point of interest? So basically, in the direction of force, my potential energy decreases here. So I got the conclusion, very important here. When we talk about the potential energy, it decreases in the direction of force. Okay, so this is what this negative sign is all about. In this respect also, we are getting the very important conclusion. This was, the kind of information. When we talk about the variation of the potential energy, we come across a number of conclusions. Okay, this was all about here. Thank you.